So today I want to talk about equations of lines and planes. Let's start with lines. Okay, so quick review of how we write down equations of lines in 2 dimensions. So if this is x and y axis, you might have seen some version of this formula. So y equals mx plus b, or maybe b plus mx. So when x is equal to 0, we'll get b, so that's the y-intercept of this line. And if we pick any 2 points on the line and compute how many units it goes in y direction divided by how many units it goes in x direction, we get the slope. Okay, so that's the meaning of the 2 constants m and b here. And this is how we usually write down the equation of a line. So let me give you another way to write down an equation of a line in 2 dimensions. So I'm going to use vectors. And here's the formula I'm going to give you. It's not too different from before. So vector r is going to be some r naught, some constant vector, plus variable t times the velocity vector v. Okay, so this is the vector version of the equation, and sometimes called the parametric equation, parametric version of the formula. And the reason why we call it that is the parameter t. So one drawback is that we're kind of introducing a new variable t, right? So we have 2 variables x and y. It's in a 2-dimensional x and y coordinates, so that makes sense. But then you're throwing in another variable t. So it looks like you're making the problem more complicated. But this version of the equation generalizes nicely to higher dimensions. So let's take a look. Basically, what we have is this. So we have 2 formula, x and y. And we start with some starting point, x naught or y naught. That's the starting point on a plane. So we start with some point x naught, y naught. And we travel in the direction of vector v. So let's say vector v is this vector AB. Okay. And we're looking at any multiple of t in the direction of vector AB. So remember, when we multiply a vector by a scalar, you could scale this, you can make this vector longer and shorter. So we're talking about all of the points in that direction. So we start with x naught, y naught, and we look at all of the points that you can reach by stretching this vector forward and also backwards. Okay. So that's the point on a line and the direction of the line. Okay. And if you kind of put this into a single formula, add and multiply each of the components, then you can get the x coordinate by x naught plus at, and y component y naught plus bt. Okay. All right. So let's take this picture, which is a little bit easier to work with, and then bring it into 3 dimensions. Okay. So we're gonna start with the vector version of the equation. So we're gonna do something similar. In fact, the formula is exactly the same as before, except you have 3 coordinates now. Sorry, there's 3 coordinates. So let me squeeze in a z there. Okay. All right. So we're going to start with the point x naught, y naught, z naught. So here's x, y, z axis. And we have some point in three-dimensional space, x naught, y naught, z naught. That's the starting point. And then we're going to have a directional vector ABC. And this is the direction that we're going to stretch into a line. So any multiple in that direction forwards and also backwards as well is going to trace out a line throughout the three-dimensional space. Okay. So this is the vector version of the, or the parametric version of the line. And you can kind of write each of the components separately as well. So you can also write it as set of equations x, y, z, and each of the component given by the formula that's there, x naught plus at, y naught plus bt, and z naught plus ct. So if you're given an equation of a line in this format, in this parametric version, so you can kind of read off how the line is drawn, right? So you look at the constant parts, and that will give you a point on a line. So you're given a point that you could start out with, and the coefficient of the parameter t, so what's being multiplied to the variable t, that's going to be the directional vector. All right. So I hope that made sense. Now let's look at like an algebraic version of this formula. So in 2 dimensions, we were able to write down an equation of a line without bringing in this extra variable t into it. So how could you write this down as a algebraic equation that does not involve like fourth variable t here? The way to go about it is to set t equals to each other. So in this formula, x is equal to x naught plus at. Take this equation and solve for t. So subtract x naught from both sides. And then divide by a. So t is equal to x minus x naught divided by a. And you could do that for each of the coordinates. So you could take the second equation, solve for t, and the third equation, solve for t. And all of these three equations are equal to t. So I could set them equal to each other. They're the same. Okay. So if you're given a formula in parametric form, you could solve for t and translate it into this equation of a line. So this looks a little bit funny, right? Because usually when we write down an equation, we just write one equal sign. So really, there's two equations kind of embedded in here. So this first expression is equal to the second thing. And each of those things is also equal to the third thing, right? So I wrote it down in one line, but really there's two equations hidden there. Okay, so that's what we're going to call symmetric equation. And if you have it in this form, you can kind of read off the point and the direction of a line as well. So x naught, y naught, z naught, what's being taken the difference of from the variable x, y, and z. These are the the coordinate of x naught, y naught, z naught on the three-dimensional space. And the denominator here is going to be the directional vector. Okay. There's one caveat that might look really different when one of the components of this directional vector happens to be 0. So let's say a directional vector looks like 0, 2, -3. So one of the component is 0 here. So this formula breaks down because obviously we can't divide by 0, right? Here's the issue. If I try to write it down, I'll be dividing by 0. But what does that mean? If the directional vector has no component in x direction, that means the x value is not changing at all throughout this line. So x is a constant here. So instead of writing it in this form, you write it this way instead, right? So if it's not changing at all in x direction, then you write x is equal to x naught, whatever the fixed value of the x is, and then the other two components, you can set them equal to each other. So that's how you'd get an equation, symmetric equation, when one of the components is 0. If two of the components were 0, then you'd have something like x is equal to x naught and y is equal to y naught. And then, so x and y is fixed, but z could be anything. So there's no restriction on the z variable. So that's what the two equation would be. Okay. All right. So I want you to be able to go back and forth between these two forms. So sometimes to solve certain problems, it's easier to have it in the parametric form or the vector form. And on some problems, it's easier to have it in symmetric equation form. So I want you to be able to go back and forth. Okay, so let's practice this. I already told you how to go from parametric version to the symmetric equation. It's to solve for the parameter t and set them equal to each other. So that's how to do that one. Let's say I'm given a symmetric form equation like this, and then I want to turn it into vector form. So what I have to do is to look at this equation and make it into this form up there. So I can rewrite this. So if there's no denominator, you can just put a 1 on the bottom. And here I have a 2 in front of a z. So if you have a coefficient in front of a z, you could, so multiplying by 2 is same thing as dividing by 1/2. And nothing is subtracted from the z, but then you're subtracting 0 from z. So now if I have it in this form, I could write down the symmetric form, sorry, parametric form. So the point that I have is 3, 1, 0. So I'm looking at these numbers right here. And the directional vector is 1, 2, 1/2. Okay. So that's in parametric form. Okay. All right. So let's do some 3D geometry with lines. So let's say I'm given two equations of lines. So let's say the first line is called L1 and the second line is called L2. And they're both given in parametric form. When we're looking at parametric form, the two parameters for each of the line does not have to be the same. So I intentionally use different letter here. So the parameter for the first line is called t, and the parameter for the second line is called s. I try to draw s so it does not look like 5. So I hope that's good. Okay, so we have lines in 3 dimensions. One interesting thing that I want to be able to answer is if they're parallel to each other. So are they kind of pointing in the same direction in some sense? Okay, so we get a parallel line when directional vectors are constant multiple of each other. Okay, so let's see if that's true. Okay, so for the first equation, I'm reading the coefficients of the parameter t. So the velocity vector or the directional vector for the first line is 1, 3, -1. And the directional vector for the second line, I'm looking at the coefficients of s here. That would be 2, 1, and then 4. Okay. These are not multiple of each other, right? So, well, just looking at the first component, if V1 was a multiple of V2, then just looking at the first component, V2 should be twice the vector V1. But if you multiply the V1 by 2, you would not get the same vector. Right? So V2 is 214. So the y and the z component does not match. So we know that this thing is not parallel to each other. Another thing that I want to be able to answer is if these lines intersect each other. So do they have a point in common? So I want you to try to imagine like 2 lines going in space. It's possible that they're not parallel and one line goes over each other, right? So if they don't intersect, they're called skew. So is it skew? So we know they're not parallel. Is it they're skewed, or do they actually hit and there's a point in common? Okay, so let's see if we can compute that. I'm gonna erase a little bit. So I have a little bit more room. Okay, so this basically boils down to question. Are we able to find t and s so the x, y, z are equal to each other? So let's see if we can set them equal to each other. So we want the x to be equal and y to be equal, and also hopefully z to be equal as well. But let's first set the first 2 variables equal to each other. So it's 1 plus t equal to 2s. Negative 2 plus 3t is equal to 3 plus s. So I want to make this true. And the reason why we're only looking at the first 2 equations is because Well, that's already two equations and two unknowns, right? We have two linear equations. So we should be able to solve for t and s here. And then let's see if the t and s is determined here. So we could solve it and plug it in to see if they match on the zth coordinate. Okay. How could we do this? Well, let's see. There's a couple different ways we could do this, but maybe I'll do it by substitution here. I'm going to take the first equation and solve for t. Okay, so t is equal to 2s minus 1. And I'm going to substitute that into the t in the second equation. Okay, let's distribute the 3. Okay, let's bring all the s to the left-hand side and all the constants to the right-hand side. Let's see, I have a 6s here, and if I subtract an s from both sides, I get 5s on the left-hand side of the equation. And then I have the constants -2 and -3 on the left-hand side. If I add 5 to both sides, I get 3 plus 5 is 8. So we get s is 8/5. Once I get s, I can plug it in here to solve for t. Let's get a common denominator. Subtracting 1 is the same thing as subtracting by 5/5. So I get t is 11/5 and s is 8/5. Okay, so what does this mean? For the two lines, for the x and y coordinates to be equal to each other, it happens exactly when t is equal to 11/5 and s is equal to 8/5. But that doesn't mean that the z coordinate is equal to each other either. So let's see if they match. So if I plug in 11/5 into the z coordinate on the first line, getting a common denominator. Okay. When the x and y coordinates are equal to each other, the z coordinate is 9/5. Now let's plug in 8/5 into the z coordinate here. I'm running out of space. Let's see, that's -15 plus 32. So that's positive 17/5. Okay. So the z coordinates do not agree. So if they agreed, they would have intersected at that point. But they didn't. So that means that line 2 has a higher z coordinate than line 1 when the x and y coordinates match. So they do not intersect. Okay. All right. I hope this problem made sense. So if you're given two lines in either parametric form or symmetric form, you can work out if they intersect with each other or not. If they intersect, then there could be a follow-up question as well. If they intersect, what angle do they make when they intersect? Well, to answer that question, first you have to make sure that they intersect. And then if they do intersect, you could use the dot product method to compute the angle between the two directional vectors. So You look at the vector v1 and v2, and then you take the dot product and use that formula, arc cosine of the dot product divided by the magnitude of each vector, and work out the angle. There's one thing that you should worry about. When two lines intersect, there's really two angles that are formed. And depending on which way the directional vector is pointing, you might get an acute angle or you might get an obtuse angle. But they're related to each other, right? We know that the angle should add up to pi radians or 180 degrees. So keep that in mind when you're computing angles between two lines. So because there's two angles, probably the thing to do is to report one of the angles, and usually you're looking at the smaller of the two angles. Anyways, I think this is a good place to stop for this video. I'll see you later.